Hi, I'm Anurag Sarkar from Northeastern University, and in this presentation I'll be talking about procedural content generation using behavior trees, or PCGBT for short. The idea being, as the name suggests, to use behavior trees for level generation rather than defining NPC behaviors, which is how they're typically used. And so why might this be a good idea? Well, behavior trees are a very widespread and commonly used technique for implementing NPC behaviors in enemy AI, having been used in a large number of commercial games. And the reason for this popularity is that behavior trees enable designing behaviors in a modular and reactive manner. So modular in that simple behaviors represented by simple trees can be combined in order to make up more complex trees representing complex behaviors. And reactive in the different branches of the tree could be selected for execution based on various runtime conditions. Additionally, as long as the trees aren't too convoluted or complex, they are fairly human readable, and you can, in many cases, just look at the tree and be able to reason about why a certain behavior pattern is being executed or what decisions led to a specific pattern of behavior. But these are all desirable qualities for procedural content generators. It's nice to have modular generators that you can combine and reuse in different ways in a generative pipeline, for example. It's also nice to have generators that can produce stuff dynamically in response to different runtime conditions, and we'd like to have generators that aren't black boxes, but where you can actually see what design decisions made by the generator lead to different content being generated. And so in this paper, for all of these benefits, we propose to use behavior trees for PCG, and a little more specifically, we explore the idea of repurposing behavior trees to model game design agents rather than game playing agents. And so instead of performing NPC actions such as find cover, for example, we replace those with design actions such as place room or generate segment. And you can think of it as simple behaviors being analogous to generating sections of levels and complex behaviors being analogous to generating whole levels. And so for the rest of this talk, I'll go over how this approach can be used to generate levels for Mario, Mega Man, Metroid, and Dungeons, and also show how we could use behavior trees for coming up with game agnostic generic level generators, as well as generators that can blend and combine levels from different games. And so just to give a quick overview of behavior trees, these are directed tree structures consisting of a root node where execution starts, a set of internal nodes which control the flow of execution, and a set of leaf nodes which define the low-level actions to be executed. The root controls execution by propagating signals called ticks at a predetermined frequency, and each node receives ticks from its parent node and propagates it to one or more of its child nodes. A node executes only if it receives a tick from its parent, and each child, after finishing execution, returns either a running, complete, or failure status to the parent, which in turn eventually gets propagated all the way back up to the root. Now, there are typically four types of internal or control flow nodes. We have sequences, which attempt to execute all of their children moving from left to right, and they return success only if all of their children succeed. We also have selectors, which pick only one of its children for execution, executing the first child from left to right that returns success, and these fail only if all of their children fail. We also have parallel nodes, which execute all of their children simultaneously and succeed if a predetermined number of children succeed, and decorator nodes, which modify the behavior of their child nodes. Leaf nodes are usually of two types. So we have action nodes shown in this figure in the gray ellipses. These execute commands corresponding to the most low-level behavior being modeled. And we have condition nodes shown using the gray diamonds, which return either success or failure based on if a certain condition is true or false. And finally, behavior trees may optionally also use a blackboard, which in its simplest form is a key value store that is globally accessible by all of the nodes in the tree and used to store information that may be useful when making decisions. And as we shall see, we make extensive use of blackboards in this work. And so how do we use these behavior trees for PCG? Well, it's pretty simple. All we do is change what the action nodes are doing. So rather than have them execute NPC or enemy behavior such as in a traditional behavior tree, here we have them perform level design tasks such as placing rooms or generating segments, for example. And this in turn requires that instead of having these action nodes refer to an underlying library of scripted actions and behaviors, we now have the action nodes refer to an underlying library of content. And this could be in the form of level segments, as in this work, or alternatively, it could also be a set of generative algorithms. But overall, as a result of this, executing an action node would now generate a part of a level rather than perform some sort of NPC behavior as in traditional behavior trees. And so at a high level, there are three main components to this PCGBT framework. There's the content library, which defines what the tree works with. In this work, these were level segments, but again, these could be generative procedures. Next is how the action nodes use this library for generating content. In this work, we had different types of nodes, sample different types of segments, but action nodes could also potentially just pick a specific generative algorithm to execute. And finally, we have the blackboard for storing information useful for level generation that can be accessed globally by all the nodes of the tree. So this can include things like the location in the game world where the next piece of content should be generated, player information, state of the game world, designer preferences, and so on. And just a quick note before going further, this work was fairly exploratory in nature. We only used sequence and selector nodes and did not perform any dynamic level generation, but we hope to do that in the future. And parallel and decorator nodes could also be used. Additionally, all branching decisions were made at random, but one could imagine these could also be made based on designer preferences or player behavior or some sort of dynamic difficulty adjustment algorithm. Okay, so with all that said, I'll now move on to discussing applications of behavior trees for generating levels in a bunch of different games, starting as always with Mario. So here for the content library, we extracted level segments from the Mario levels in the VGLC, and then we categorized them based on the design patterns that were contained in the segments using the design patterns as defined in prior work by Dalskog and Togelius. The action nodes were then defined to take one or more of these patterns as parameters and sample a segment that contained at least one of these patterns. And then after placing the segment at the current location in the level, it would increment the x direction on the blackboard by 1 since Mario levels progress exclusively to the right. Okay, so here's a step-by-step example to illustrate how exactly a level might be generated using this approach. So we start with two very simple trees, each with one leaf node. The first places the staircase segment, while the second places the segment containing this valley structure made up of two pipes. Next, we build on each tree, so an action node placing a stair valley segment is added to the first tree to get this section of stairs, and then to the second tree we add two additional pipe valley action nodes to get this section filled with pipes. We then combine these two separate trees by having them both be children of a new root sequence node, and that gives us this level with a section of stairs followed by a section of pipes. And we could just keep this going and keep adding extensions to generate new trees, such as the two example trees we have here, where in the first we add a section of enemies by adding another action node to the right, while in the second one we add a new sequence node to the left, which in turn generates some additional level segments at the beginning. And so hopefully from this example we can see how behavior trees could model level generation and how these simple trees corresponding to smaller sections of levels could be combined and built up to generate larger complete levels. So here's another example, this demonstrating the use of selector nodes, shown using the blue octagons for picking between different branches of execution. So after a random initial segment is generated, the first selector decides whether to generate a section of paths and pipes or a section of stairs and enemies, while the second decides between a section with gaps and a section with valleys. The decision to branch is made in the condition leaf nodes shown using the gray diamonds. For these examples, these choices were made randomly, but we could have, for example, used selection probabilities weighted by designer preferences. Also, in a dynamic setting, player data could be used to make this choice. So for example, in the do gap condition node under the second selector, we could check if the player has already lost a certain number of lives and then generate valleys instead of gaps to reduce the difficulty. Okay, so that's all for Mario. Next we have Mega Man. So here, similarly, the content library was made up of segments extracted from VGLC levels, but here we group the segments based on the directions in which they were open, that is, in which directions movement was possible, and accordingly tag the segments with up, down, left, and or right. Action nodes were then defined to take one or more directions as parameters and sample a segment that was open in those directions. Additionally, since levels in this case can progress in multiple directions, action nodes also checked if an opening existed between the sample segment and the previous segment, and if this didn't exist, it would resample until it found one that did. And then it updated the XY coordinates on the blackboard accordingly based on the direction. And so here's an example for Mega Man. So this tree generates an initial horizontal section, then decides between generating a horizontal or a vertical section, followed by a middle horizontal section, a vertical section, and then a final horizontal section. Note also that each vertical section is generated by a selector that decides whether the section will progress upward or downward. And this just goes to show that the same behavior tree can produce fairly different looking levels while sticking to an overall structure set by the tree. So moving on to dungeons, in this case, we implemented behavior trees for generating layouts for Zelda-style dungeons, and the motivation for this was, well, we want to try this approach for genres other than platformers like Mario and Mega Man, but also we want to test out other features of behavior trees when used for generation. So in the previous two cases, in both cases, the behavior trees were all generated using a single tick of the root node, and so we wanted to test using multiple ticks as is more typical of behavior trees. Additionally, due to the linear nature of the Mario and Mega Man levels, we used a very linear generative process, and so by generating dungeons, we wanted to test a more non-linear generative approach where levels have to sort of loop around and not always follow a strictly linear path from start to finish. So for this case, the content library consisted of rooms extracted from the Zelda levels in the VGLC. And then each room was tagged with the directions in which it contained doors, and the action nodes then sampled a room from the set of rooms that had doors in the desired directions as determined by a simple layout algorithm, details of which were given in the paper. So here's the behavior tree for generating dungeon layouts along with two sample dungeons. So unlike previously, the behavior tree here runs for multiple ticks and generates one room per tick, executing a loop of ticks until all rooms have been generated. For this, we store a flag on the blackboard to indicate if the start room has been generated, and this is initialized to false, and then during the first tick, the start selector executes, generates the starting room, and disables the flag so that on subsequent ticks, this check fails. Note that the Mario and Mega Man trees could also have been implemented using a loop of ticks, and this dungeon tree could have been implemented using a single tick. But we're just demonstrating the different ways in which behavior trees could be used for level generation, and these design choices mostly come down to preference and what works best for a specific game. Next, in addition to modeling level generators for specific games, we wanted to make these game agnostic or generic behavior trees where the same tree structure could generate levels for multiple games. Now, this only requires that the sections generated by the control flow nodes and the segments produced by the action nodes are compatible across multiple games. And in fact, we've already seen two such behavior trees. While the Mario behavior tree is non-generic because it utilizes Mario-specific design patterns, the Mega Man behavior tree could generate levels for any platformer that consists of vertical and horizontal sections and segments with openings in 4 directions. Similarly, the dungeon layout behavior tree could be used for any game with interconnected segments. And so Metroid, being a platformer and having a sprawling interconnected game world, satisfies both these criteria, and so we tested generating Metroid levels using the same behavior trees that we used for generating the dungeons and the Mega Man levels. So here's the same dungeon layout behavior tree from before, but this time the action nodes are working with Metroid segments rather than Zelda rooms. And just with that change, the same exact tree can now generate these Metroid levels, such as the one shown here. Similarly, here's a behavior tree adapted from the prior Mega Man tree, along with an example Metroid and an example Mega Man level, both generated using it. So essentially the tree is just switching which content library it interacts with. So for generating Mega Man levels, it has the action nodes work with Mega Man segments, and for generating Metroid levels, it works with the Metroid segments. With the same tree, could be used for generating levels for both of these games. And finally, for the last application, we have blending. So the idea here is that given that subtrees corresponding to different level sections could be combined to form larger trees for generating whole levels, one could combine a tree for generating levels of one game with a tree for generating levels of another to produce a more complex tree that can then combine sections taken from different games and produce these sort of blended levels. So um, the example tree here consists of an initial sequence for generating a Mario section, followed by a selector which generates either a horizontal or a vertical downward Mega Man section, followed by a sequence for generating a horizontal and then a vertical upward section of Metroid. And so some takeaways, our results suggest that behavior trees can in fact be repurposed for modeling design agents and generate levels for several games and give us these modular and interpretable generators. And just to clarify, note that this notion of PCGBT is not proposing a specific algorithm or behavior tree implementation, but simply referring to the use of behavior trees for modeling procedural level generators. The implementations of the condition and action nodes are agnostic to the PCGBT framework, and it's in fact important to decouple the framework from underlying implementations in order to enable the approach to generalize to multiple design styles and preferences. Overall, the primary utility of this approach is to enable designers to combine handmade and generated content into whole levels in a modular, explainable, and potentially dynamic manner. Speaking of which, just want to briefly touch on some potential research directions, which we talk about in a little more detail in the paper. So in the future, we could try this approach in a dynamic setting where different level sections are generated by choosing different branches based on runtime conditions. And in this case, we could have conditions tied to player behavior and generate different levels and gameplay experiences specifically tailored towards different player types and difficulty levels, for example. Another interesting direction would be to see if we can combine traditional game playing behavior trees with these game design trees that we've been looking at. So, for example, it may be possible to come up with hybrid behavior trees where there are separate branches for game playing and game design. Perhaps the game design branch could generate a level section, and then a traditional game playing branch could try to play that generated section to test for playability. We could also explore evolutionary algorithms for applications such as co-evolving game playing and game design agents using the same behavior tree formalism. Speaking of evolution, there has been a lot of prior work that uses evolution as well as reinforcement learning for generating traditional behavior trees. So we could look into applying these techniques for level generation behavior trees. One use case might be to use these techniques to infer and or evolve tree structures from a set of exemplar levels. And finally, general game design or general level generation is the idea of generating levels for a number of different games using the same generator. And we've seen that PCGBTs are capable of this via the generic and blend examples. And so could we in the future use this to generate games dynamically at runtime? So for example, if we had a player model, we might then be able to generate different games dynamically based on the player's preferences. And similarly, could we use the blend behavior trees in a dynamic setting to switch different games in and out over the course of gameplay? So those were more long-term research directions. I'll conclude with some immediate future work possibilities. So in the future, we want to perform more rigorous playability evaluations as well as expressive range analyses for different trees. Something I've touched upon multiple times during this talk is we want to try applying these behavior trees for dynamic level generation and also look into having action nodes generate content from scratch rather than just sample existing content. And additionally, we'd also like to develop some sort of GUI or interactive application to enable designers to create and combine their own behavior trees, as well as conduct a user study to evaluate the player experience of levels generated using this approach. And that brings me to the end of this talk. Thank you for your attention.